Okay, so now we've talked about how antibiotics work. We've talked about different types of organisms they can kill. So let's talk about a little bit of like some tests to guide chemotherapy. Testing effectiveness is used to determine which antimicrobials will inhibit the microbes causing a specific infection. We talked about Kirby-Bauer tests a little bit when we talked about Chapter 7. This is also something we get to do in lab towards the end of our lab exercises. The minimum inhibitory concentration is the lowest concentration that inhibits the visible growth of bacteria. We tend to want to give a lower dose, as low a dose as we can, to completely knock out that infection, but keeping it at a lower dose reduces the risk of side effects. And then a minimum bactericidal concentration is the lowest concentration to kill 99.9% of the starting inoculum. Okay, oral drugs are typically the way that we prefer to administer drugs. That means you can write a prescription, or patients can take them at home. Topical preparations are used to treat superficial or just on the surface of the skin. But then IV and intramuscular injection sometimes will be used if a patient can't take an oral medication. So if they are vomiting, if they're intubated, you're going to need to give them a drug, either IV or intramuscular. Somehow parenterally, they're going to need to be given it. And then the most terrifying thing we talk about in this class, I think, is antimicrobial resistance. So the first time a drug is given, there's very little resistance in the population. They're very susceptible, so mortality rate is going to be very high. But there will be a few survivors. You know what those survivors are going to do? They're going to have all the space to grow. They're going to eat all the food that was there being eaten by the susceptible cells. So before long, all you have left are resistant cells. The reason they're resistant is just random mutations will pop up in different cells, just random genetic differences. There also could be a plasmid that they're carrying that gives them drug resistance, and that plasmid could be shared through conjugation or through transduction. So when we give an antimicrobial to a patient, you want to give enough of that drug to kill all of the population. You don't want to just give enough drug until they start to feel a little better, and then they quit taking the drug, but then they have a little bit of resistant cells left. You want to give enough of a concentration to knock out all of the cells, reduce the risk of having any survivors to lead to any sort of resistance. Different ways that a bacteria can gain resistance to an antibiotic. One is by blocking entry. So whatever target that antibiotic is using to get into the cell, whatever porin is there, the cell just modifies its porin, and suddenly that antibiotic can't get into the cell. One is by destroying or inactivating the drug. We talked about penicillinase, how it can cleave penicillin. One is by altering the target membrane or the target molecule. So we talked about how some antibiotics can target different things like an enzyme, that if you change the enzyme, it'll have a different ability to bind to the antibiotic. And one is by efflux. We have already used that word in this chapter. Bacteria have efflux pumps that they can use to eliminate toxins, and they just pump that antibiotic right out with all the other toxins. So here we have an antibiotic should be able to get into the cell instead of just bounces right back out because it's not able to get in. Here is enzyme inactivating it. So this antibiotic just cleaved in half. Here, this antibiotic should be able to interact with this molecule here, but this molecule has changed shape now, so it can't interact. So this antibiotic can't work. And then this last one is efflux. It gets in and bounces right back out. Nice little bouncer, kicks it out. Misusing antibiotics will select for resistance to develop mutants, for resistant mutants to develop. Misuse would include using outdated or weakened antibiotics. Don't do it. Using antibiotics for the common cold or other inappropriate conditions. Antibiotics are not going to kill a virus, so don't do it. Putting antibiotics in animal feed. This used to be commonly used, although over the last several years, there have been more crackdowns and laws against just routinely putting antibiotics in animal feed. It used to be very easy to just go into any farm and find antibiotic resistant bacteria all over their barn. So by reducing that antibiotic usage, it greatly reduces antibiotic resistance bacteria. One is by failing to complete the prescribed regimen. So you gave me a 10-day prescription, but after 5 days, I feel better and I just don't finish my prescription. And then using someone else's leftover prescription, which could likely include all of the above, well, except for 3. It could involve outdated, weakened antibiotics, inappropriate conditions, and not taking the full regimen. All of these are going to select for antibiotic resistance. So do not do these things when you take antibiotics. And when you are a healthcare provider, properly educate your patients so that they are not doing these things. All it takes is one superbug to, cause a massive infection that we can't prevent, and it could cause who knows how much harm. Okay, last thing to talk about is combining drugs together. So, if you have one drug and another drug and you put them together, they should just be able to do their business, right? But sometimes if you put 2 drugs together, they're going to have what's called synergism. So together, they just start working overtime. Have you ever been in like a meeting where you just bounce ideas off of each other and you bring out the best in each other? You just come up with even more ideas than if you were working alone. That's what synergism is. So here we have this drug should be able to kill the bacteria only within the circle. This drug should be able to only kill the bacteria within the circle. But when you put them together, this aztreonam and the amoxicillin with clav acid, suddenly they're killing bacteria outside of the circle. They're killing even more. So this whitiness is where the bacteria is. This clear zone, you can see extra bacteria being killed. That's synergism at work. Antagonism is when 2 drugs together work less effectively than either one alone. So if you've ever thought of like 2 kids in the back seat of a car on a long car trip will antagonize each other, instead of spending their time, reading their book, learning, doing great stuff, being good little taking care of mother or whatever, they just spend their whole time bickering, fighting with each other. It's kind of what the drugs are doing. They just spend their whole time fighting against each other instead of fighting against the infection. So antagonistic drugs are not going to be effective if you take them together. So if you are prescribing drugs, you need to keep in mind if you are using drugs that can be synergistic or if they can be antagonistic. Probably you want to just avoid drugs that are going to impact the other one's activity, but at least keep in mind if you cannot get away from putting them together, be informed about how they could affect each other together. Okay, in the future, we have future ways that we are going to be trying to do chemotherapy to treat infections. Those would include targeting virulence factors. So instead of just killing the bacteria, just attack that specific virulence factor. Leave your normal microbiome alone. One would be sequestering iron. Iron is used to feed the pathogen. Without the iron, the pathogen doesn't grow. One is by using bacteriocins. These are just antimicrobial peptides produced by bacteria. One is phage therapy. Phage therapy was actually studied a lot before penicillin came out as a drug. And now it's kind of regaining some popularity in studies. You can easily find a lot of research about phage therapy now, using a virus to kill a bacterial infection. It would come along with a little bit of patient education. I don't think you could really just say, oh, you're sick, here's a little pill made of viruses, and most people would kind of look at you funny. But I think that's a fabulous target. One is exploiting our microbiome. So, how is our microbiome protecting itself from infections? How is it trying to inhibit the growth of pathogenic bacteria? Just exploit it to protect ourselves. And then one is antimicrobial peptides. Antimicrobial peptides are short little antibiotics made by plants and animals that are typically bactericidal, typically have a broad spectrum of activity, and are part of the natural defense system of a lot of forms of life. And then we have antisense agents. These are short little pieces of DNA that can block the synthesis of bacterial toxins. And RNA interference and small interfering RNAs, where you can stop gene expression by using this siRNA, which binds to the messenger RNA. And when it binds to the messenger RNA, it makes double-stranded RNA. Our cells don't like double-stranded RNA, and they break that down. So that will stop the production of that messenger RNA. Okay, so now you can tell me, what is the most common mechanism that a bacteria uses to resist the effects of penicillin? And what are antimicrobial peptides? All right, I will see you later. That's it for chapter 20. If you have any questions preparing for your next exam, please feel free to contact me. I hope you are able to do your very best. Show me everything you've learned. And I'll talk to you later. Bye.